There's something out there that shouldn't exist. You're looking at an object 440 meters wide. Racing through our solar system at 186,000 miles per hour, NASA's test satellite stacked over 9000 images of it, 9,000 frames, designed to reveal even the faintest whisper of structure. The result: a point, a dot, no tail, no glowing coma spreading across space. Nothing but a pinpointed light where a comet should be screaming across the heavens, with a tail millions of miles long. And yet, the James Webb Space Telescope is detecting water vapour and carbon dioxide pouring off this object in massive quantities. Ground-based spectrographs are screaming that volatiles are escaping into space. So you're forced into an impossible corner. Either every instrument we've built is lying to us in perfect coordination, or we're staring at something that breaks the fundamental physics of what comets are supposed to do. On October 14th, 2025, the data dropped. The contradictions became undeniable. And tonight, we're going to walk through exactly why 3I/Atlas has astronomers questioning everything they thought they knew about interstellar visitors. If you value deep dives into cosmic mysteries that actually matter, consider liking and subscribing when you genuinely find it worth your time. Let me know in the comments where you're tuning in from. Now, let's unravel this. So let's start with what TESS actually did, because understanding the method makes the failure so much more profound. TESS, the Transiting Exoplanet Survey satellite, wasn't designed to hunt comets. It was built to find planets around distant stars by detecting tiny dips in starlight when those planets pass in front of their host stars. But its cameras are exquisitely sensitive to faint objects. And when 3I/Atlas came barreling through our neighbourhood, astronomers pointed TESS at it. Over the course of several weeks, TESS captured 134 individual images of this interstellar visitor. Think about that number for a second. 9,134 frames. That's not a casual glance. That's surveillance-level observation. Now here's where it gets technical, but stay with me because this is the heart of why the results are so devastating. The astronomers used a technique called co-adding. Imagine you're trying to hear someone whisper in a noisy room. One recording won't cut it, but if you record that whisper 1,000 times and layer all these recordings on top of each other, the whisper gets louder while the random noise cancels itself out. That's co-adding. You're stacking light from 9000 frames, adding photon upon photon, until even the faintest wisp of structure, a tendril of gas here, a stream of dust there, becomes visible. When the team ran their analysis, they measured something called the radial brightness profile. It's exactly what it sounds like. How bright is the object at its centre? And how does that brightness fall off as you move outward for a star, which is essentially a point infinitely far away? The brightness drops sharply. There's no actual extension. It's just the star's light smeared by your telescope's optics. For a comet, the profile is different. You see a bright nucleus surrounded by a diffuse glow, the coma that fades gradually. The tail stretches even farther, sometimes millions of miles, catching sunlight and creating that iconic streak we've been drawing in cave paintings for millennia. 3I/Atlas's profile, it dropped like a star. Point source, no extension, no coma halo, no tail. Let me put this in perspective. 2. Halley's Comet. When it visited us in 1986, had a tail stretching 60 million miles across space. Comet Hale-Bopp in 1997 had 2 tails, one of dust, one of ionized gas, each visible from Earth with the naked eye. Even small, faint comets show structure when you image them properly. The whole definition of a comet is that it's an icy body that, when heated by the sun, releases gas and dust into space, creating that characteristic fuzzy appearance. If you don't see that fuzz, you're not looking at a comet, you're looking at an asteroid, except 3I/Atlas can't be an asteroid either, because other instruments are detecting gas, lots of it, water vapour, carbon dioxide, the chemical signatures of a violently active object. So you're stuck in this impossible position optically. It looks dead. Spectrally, it's screaming with activity. The technical term for what Tess measured is the point spread function, or PSF. Every telescope has one. It's the fingerprint of how your optics blur a point source of light. When you point a telescope at a star, you don't see an infinitely small dot. You see a fuzzy blob whose shape is determined by your mirror's imperfections, atmospheric turbulence, and the fundamental physics of light diffraction. That blob, that pattern, is your PSF. When Tess looked at 3I/Atlas through 9000 stacked frames, it saw only its own PSF, nothing beyond it, no extended structure whatsoever. The team could actually quantify their detection limits. They could say, if there had been dust with a surface brightness greater than X spread over an area larger than Y, we would have seen it. The signal-to-noise ratio after stacking 9000 frames was high enough to detect incredibly faint features, things 1,000 times dimmer than you could see with a single image. And they saw nothing. Here's what keeps me awake. This shouldn't be possible. The physics of cometary activity is well understood. When ice sublimates, when it turns directly from solid to gas without melting, it releases dust particles that were frozen inside the ice. Those particles get pushed away from the nucleus by radiation pressure and solar wind. They scatter sunlight. They create the tail. This isn't speculative. We've seen it happen on every single comet humanity has ever observed up close. We've sent spacecraft to comets. We've landed on one. We know how they work. But Tess is telling us that 3I/Atlas isn't doing that. Or it's doing it in such a bizarre, confined way that the dust never escapes far enough to become visible. Imagine a fire that produces heat and light and chemical combustion but no smoke. Not because the smoke is invisible, but because it somehow never leaves the flames. How would you even build a model for that? The data is public. By the way, anyone can download the TESS observations, run their own co-adding analysis, check the math. Multiple independent teams have done exactly that. The results are reproducible. This isn't a processing artifact or an instrumental glitch. 3I/Atlas genuinely appears as a point source in optical wavelengths after 9000 frames of observation designed specifically to reveal faint extended structures. Now, you might be thinking, okay, maybe it's just a weird comet. Maybe the dust is unusually compact, or maybe the particles are too small to scatter light efficiently. But here's the thing, we can test those ideas. Small particles scatter light differently than large particles. Compact dust should still show up at some level when you stack 9000 images. The test team derived constraints on particle size, dust density, and ejection velocity based on their non-detection. And those constraints are brutal. To remain invisible at Tess's sensitivity level, the dust would need to be confined within a radius so small, just a few hundred kilometers from the nucleus, that you'd need some kind of force actively holding it there. Gravity alone isn't enough. Radiation pressure would blow it away. Something else would have to be trapping that dust. And before you say, maybe there's just no dust, only gas. Remember that ice doesn't sublimate cleanly. When water ice turns to vapour, it carries dust particles with it. That's how comets work. The only way to get pure gas release without dust is if your object is made of pure volatile ices with no embedded particles. And that's geologically implausible. Comets form in regions of the protoplanetary disk where dust and ice mix. You don't get pure ice bodies at the scales we're talking about, so the test data leaves us with three possibilities. None of them comfortable. First, there's dust. but it's being confined by some mechanism we don't understand electromagnetic effects. Maybe, or some exotic form of plasma behaviour. Second, the composition of 3I/Atlas is fundamentally different from any comet or asteroid we've ever studied, made of materials that don't behave according to our models. Third, what we're looking at isn't a natural object at all. I want to be crystal clear here. I'm not saying it's aliens. I'm saying the observations are forcing us into a corner where we either have to invent new physics to explain a comet, or we have to seriously consider that our basic assumptions about what this object is might be wrong. And that's uncomfortable. Scientists don't like being uncomfortable. We like things that fit our models. We like predictable behaviour. 3I/Atlas is not giving us that. The contradiction sits there, undeniable. Tess says point source, no tail, no extended structure. Meanwhile, every other wavelength is screaming that something active is happening. And we're going to dig into exactly what those other instruments are seeing, because when you put all the pieces together, the picture that emerges is even stranger than a missing tail. So if Tess is telling us there's no visible dust, what exactly are the other instruments seeing? Because this is where the story stops being just weird and starts becoming genuinely disturbing. Picture the James Webb Space Telescope, humanity's $10 billion masterpiece of infrared astronomy, swiveling its golden mirrors toward 3I/Atlas. JWS doesn't see the way your eyes see. It operates in the infrared spectrum, looking at wavelengths of light where heat signatures appear, where molecules vibrate and rotate and emit their own faint glow. When JWST looked at 3I/Atlas, it detected something unmistakable: water vapour, carbon dioxide, a gas coma rich in volatiles pouring off the object. The spectroscopic data was clear. Emission lines at specific wavelengths that correspond to H2O and CO2 molecules. These aren't ambiguous signals. They're chemical fingerprints as distinct as your DNA. The molecules are there. They're being excited by sunlight, vibrating at characteristic frequencies, radiating in the infrared. JWST is, quite literally, listening to these molecules sing, and the song is loud. Sphere-X, another infrared mission, confirmed the findings and added something even stranger. The ratio of carbon dioxide to water vapour around 3I/Atlas is unusual even by the standards of weird comets. In most comets, water dominates. You get roughly 10 to 20 parts water for every part CO2. It makes sense, water ice is the primary component of most cometary nuclei. But Sphere-X data suggests 3I/Atlas has a much higher proportion of carbon dioxide than we'd expect. It's not impossible comets from different regions of a protoplanetary disk can have different compositions, but it's adding another layer of strange to an already bizarre object. Now, you might be thinking, okay, so infrared sees gas, optical sees nothing. Maybe one of them is wrong, but here's the thing, they're both right. They're just measuring completely different things. JWST doesn't need to see reflected sunlight to detect a coma. It's not looking for dust scattering photons back at us. It's detecting the molecules themselves as they emit infrared radiation, even if there were zero dust particles around the nucleus. JWST would still see the gas. Optical telescopes are the opposite. They need dust. They need particles floating in space that can catch sunlight and redirect it toward our cameras. No dust means no optical signal, even if the object is vomiting gas. So the question becomes, how do you get massive gas production without corresponding dust production? Here's the problem. When ice sublimates, when it goes directly from solid to gas without melting, it doesn't leave the dust behind in a nice, tidy pile. The gas drags the dust with it. Imagine dry ice sitting on a table. As it sublimates, you see that ghostly fog rolling off the surface. Now imagine tiny particles embedded in that dry ice. As the CO2 turns to gas, those particles get carried away in the flow. That's how comets work. The sublimating ice creates pressure, and that pressure ejects dust along with the gas. You can't have one without the other unless something very specific is happening with your ice-to-dust ratio or your particle size distribution. The only ways to produce gas without visible dust are uncomfortable. First possibility, the dust particles are extremely small, sub-micron sized, and they scatter light so inefficiently at optical wavelengths that even 9000 stacked TESS images can't detect them. But particles that small should show up in other ways. They'd create specific scattering patterns in ultraviolet or polarized light. Second possibility, the dust is being held close to the nucleus by some force gravity. Maybe. Or electromagnetic effects, and never escapes far enough to become visible as an extended structure. But 3I/Atlas is only 440 meters across. Its gravity is negligible. You could jump off its surface and reach escape velocity, so gravity isn't holding anything. Third possibility, the composition is genuinely alien. Maybe 3I/Atlas formed in a region of its home star system, wherever that is, where ice and dust separate in ways we've never observed in our own solar system. Maybe it's almost pure volatile ice with very little embedded dust. That would explain the gas without the tail. But it creates a new problem. How do you form an object like that? Every formation model we have for comets involves dust and ice mixing together because they condense from the same protoplanetary material. You'd need very specific temperature and pressure conditions to create a clean ice body, and we don't have evidence those conditions exist in planet-forming regions. Let me give you a sense of the scale of this contradiction. When NASA's Deep Impact mission smashed a projectile into Comet Tempel, one in 2005, the impact excavated material from beneath the surface. Cameras watching from the spacecraft and from Earth saw a massive plume of dust and gas erupt from the impact site. The dust-to-gas ratio was about 1:1 by mass, roughly equal amounts of dust and vaporized ice. That's typical. Comet 67P/Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 years, showed the same pattern. Gas jets erupting from the surface always carried dust. Always. The European Space Agency's cameras captured it happening in real time. The dusty material would coat the spacecraft's solar panels, requiring periodic orientation changes to keep power levels up. 3I/Atlas is apparently breaking this rule. JWST is detecting gas production rates consistent with active outgassing, meaning significant amounts of volatiles escaping into space. But TESS, after stacking 9000 optical images, sees no corresponding dust. It's like watching a smokestack pump out heat and exhaust gases while producing zero visible smoke. Physically, it doesn't make sense. Now let's talk about geometry, because maybe the angle matters. The phase angle, the angle between the Sun, the object, and Earth changes how we see comet structures. If a tail is pointing almost directly toward us or away from us, it gets foreshortened. Imagine a pencil if you look at it from the side. It's long and obvious. If you look at it end-on, it's just a dot. Could 3I/Atlas have a tail that's geometrically hidden from our viewing angle? The problem is that TESS observed continuously over weeks, and 3I/Atlas was moving. The geometry was constantly changing. If a tail existed and was hidden at one angle, it should have become visible as the object moved relative to Earth and the Sun. The fact that it remained a point source through all those observations suggests geometry isn't the answer. Plus, the coma, the fuzzy cloud around the nucleus, should be visible from any angle. You can't hide a coma with geometry alone. Different instruments also observed at different times. JWST had specific observation windows. Ground-based telescopes tracked the object during other periods. TESS stared continuously but with lower spatial resolution. What if the object is intermittently active? What if it's pulsing out gas and dust in bursts, and different instruments just happen to catch it during different phases? That's an interesting idea, and we've seen it before. Comet 29P/Schwarzmann-Wachmann undergoes sudden outbursts where it brightens dramatically for a few days, then fades back to quiescence. If you only observe during an outburst, you think it was violently active. If you only observe during quiet periods, you think it was nearly dead. Could 3I/Atlas be doing something similar? But on shorter timescales, the timing doesn't quite work. TESS observed for weeks. If the object were pulsing with activity, those pulses would need to be shorter than TESS's integration time per frame, or TESS would have caught at least some frames showing extended structure. We're talking about pulsations on the order of minutes or hours, which would be extraordinarily unusual for a cometary body. Comets don't typically turn on and off that fast. Their activity is driven by solar heating, which changes gradually as they approach or recede from the Sun. Here's what really bothers me about the cross-instrument contradictions. They're not subtle. This isn't a case of one telescope measuring 10% more flux than another, and scientists arguing about calibration. This is a binary split. TESS sees a point source emphatically, reproducibly. After 9000 frames, JWST sees vigorous gas production unambiguously, with clear molecular signatures. Ground-based optical telescopes see asymmetries or, in some cases, almost nothing. Meanwhile, infrared instruments are reporting large-scale volatile release. These aren't compatible observations, they're describing different objects. Have you ever had 5 people describe the same event to you and gotten 5 completely different stories? That's what this feels like. Except these aren't people with biases and faulty memories, they're billion-dollar instruments designed to measure reality with precision. And they're all working correctly. The TESS team can prove their no-tail finding is solid. The JWST team can prove their gas detections are real. The data is reproducible. The instruments are functioning as designed. So what gives the uncomfortable answer is that we might not be looking at measurement error. We might be looking at an object whose behavior genuinely doesn't fit into the framework we've built for understanding comets and asteroids. Every model we have assumes certain things about how dust and gas interact, about how sublimation works, about the structure of icy bodies. If 3I/Atlas is violating those assumptions, then we need to either expand our models, which means invoking new physics or exotic compositions, or we need to consider that our basic classification of what this object is might be wrong from the start. And here's where the story takes another turn, because there's one instrument that might have had the perfect view to resolve all of this, the perfect resolution, the perfect geometry, the perfect proximity to see what 3I/Atlas actually looks like up close. NASA's Psyche spacecraft was out there, travelling through the same region of space. Its trajectory might have brought it within imaging range of 3I/Atlas. And if it captured photographs, they could settle this entire debate in an instant. So the obvious question becomes, where are those images and why haven't we seen them? Let's talk about NASA's Psyche spacecraft. Because if there's one thing that could cut through all the confusion we've been discussing, it's a high-resolution image taken from relatively close range. And Psyche might have been in exactly the right place at the right time to capture that image. Psyche launched in October 2023 on a mission to study 16 Psyche, a massive metal-rich asteroid orbiting in the main belt between Mars and Jupiter. It's not expected to arrive at its target until 2029. But here's the thing about interplanetary missions: the spacecraft doesn't just shut down during the cruise phase. It's equipped with cameras specifically, a pair of multispectral imagers that can capture detailed photographs in multiple wavelength bands. And during the long journey to the main belt, mission teams routinely point these cameras at targets of opportunity, calibration images, navigation checks, sometimes just bonus science because, hey, you've got a camera floating through space, why not use it? NASA has released some of these cruise phase images publicly. Earth and the Moon from various distances, looking stunning and alien as the spacecraft receded. Starfields for navigation calibration, Jupiter during a distant flyby. This is standard operating procedure. Interplanetary spacecraft are constantly imaging their surroundings, both for engineering purposes and to gather opportunistic science data when interesting objects pass through their field of view. Now, here's where the timeline gets interesting. Based on publicly available ephemeris data, the precise positions and trajectories of both Psyche and 3I/Atlas over time, there are windows in October 2023 when the interstellar visitor would have been within potential imaging range of Psyche's cameras. We're not talking about a close encounter like a spacecraft flyby, but close enough that a targeted observation with Psyche's images could have resolved the object better than any Earth-based or Earth-orbiting telescope. We're talking about spatial resolution potentially down to tens or hundreds of meters per pixel, enough to see shape, enough to see structure, enough to definitively answer whether this thing has a tail or not. So the obvious question, where are those images? NASA maintains extensive archives of raw mission data through the Planetary Data System PDS for short. It's a publicly accessible repository where scientists and citizen researchers can download raw frames from spacecraft missions, sometimes years or even decades after the data was captured. This is how amateur astronomers occasionally discover new objects in old images, how researchers go back and find things that were missed during the initial analysis, comets hiding in the background of images taken for completely different purposes, asteroids passing through the frame unnoticed until someone reviews the archive. The raw images from Psyche's instruments should be findable. They should be catalogued. There should be metadata information about when each image was taken, what the target was, what the camera settings were. And yet, there's been no public release of Psyche images showing 3I/Atlas during the relevant observation windows. No announcements, no papers, no press releases, nothing. Now, before we jump to conclusions, and I know exactly where your mind is going, let's walk through the completely benign explanations, because there are several, and they're all perfectly plausible. First, bandwidth constraints. Deep space communication is expensive. Literally. You're beaming data across hundreds of millions of miles using NASA's Deep Space Network, a limited resource shared by multiple missions. Every hour of communication time has to be scheduled, prioritized, and justified. Engineering telemetry comes first because mission teams need to know the spacecraft is healthy. Primary science data comes second because that's what the mission was funded to collect. Everything else, bonus observations, opportunistic images, calibration frames gets downloaded when bandwidth is available. If Psyche captured images of 3I/Atlas, those frames might still be sitting in the spacecraft's onboard storage, queued for transmission during a future communication window. Second, data management issues. Spacecraft have limited memory. They use ring buffers essentially. They overwrite old data with new data when storage fills up. If 3I/Atlas images weren't flagged as high priority, they might have been compressed heavily to save space, or even overwritten entirely by later observations. This happens more often than you'd think. Not every frame captured by a space mission makes it back to Earth in full resolution. Some data gets lost simply because storage is finite and priorities shift. Third, metadata problems. The images might exist in the archive, but they're not properly catalogued. Anyone who's worked with large astronomical databases knows this pain. Wrong timestamps, mislabeled target fields, corrupted file headers. An image of 3I/Atlas could be sitting in NASA's planetary data system right now, labelled as a calibration frame, or star field, waiting for someone to actually look at it and realise what's in the frame. Fourth, embargo periods. Space agencies have policies about data rights. Mission teams often get exclusive access to their data for a certain period, sometimes months, sometimes longer before it's released to the public. This protects the people who spent years designing and building the instruments, giving them time to analyse the data and publish their findings without getting scooped by other researchers using the same observations. If Psyche did capture images of 3I/Atlas, the mission team might be analysing them right now, preparing papers for peer review, planning a coordinated release. All of these explanations are reasonable. None of them require conspiracy or deliberate suppression. They're just the normal friction of how space missions operate. But here's the uncomfortable part: we don't actually know which explanation is correct. We can't see into NASA's archives. We can't check the spacecraft's memory. We don't have access to mission logs that would tell us what was captured, when, and what priority it was assigned for downlink. What we can do is ask. And this is where things get practical. The Freedom of Information Act FOIA exists precisely for situations like this. US. Citizens and organizations can file FOIA requests to compel the release of government-held data, mission logs, instrument activity reports, downlink schedules, image catalogs. These documents exist. They're part of the official record, and they can be requested. Several researchers and citizen science groups have begun filing exactly these kinds of requests, not because they assume NASA is hiding something, but because transparency in publicly funded science is important. If Psyche captured images of 3I/Atlas, and those images are sitting in an archive somewhere, the public has a right to see them. If the images don't exist, we deserve to know why a spacecraft with functioning cameras didn't capture what might be the most significant astronomical observation of the decade. And if the images exist but can't be released for some reason, we deserve to know what that reason is. Think about the implications of each scenario. If the images exist and get released, we could resolve the entire TESS versus JWST contradiction in one shot. High-resolution photos would show us the object's actual shape, whether it has a visible coma, whether there's any extended structure that Earth-based telescopes are missing. We'd finally know if this thing looks like a comet, an asteroid, or something else entirely. If the images don't exist because they were never captured, that raises different questions. Why wouldn't mission planners prioritize imaging an interstellar visitor passing through Psyche's neighborhood? Was it a resource constraint? A scheduling conflict? Did they simply not realize the opportunity until it was too late? These are legitimate operational issues. But they are also frustrating given how rare interstellar objects are. We've detected exactly 3, 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I/Atlas. Missing the chance to image one from a spacecraft is a missed scientific opportunity that won't come around again. And if the images exist but are being held for reasons we don't understand, then we're in murkier territory. There are legitimate reasons to embargo data temporarily protecting mission team publication rights, verifying data quality, conducting security reviews if there's dual-use technology involved. But extended delays without explanation start to look like something else. They start to look like the kinds of information management decisions that institutions make when they're not sure how to handle something unusual. Here's a relevant historical parallel: the Oumuamua case. When that first interstellar visitor was discovered in 2017, there was a rush to observe it before it left the solar system. Telescopes around the world pointed at it. Data came in. And then Harvard astronomer Avi Loeb published a paper suggesting that Oumuamua's trajectory and acceleration couldn't be explained by natural outgassing, that it might be an artificial object, possibly a light sail from another civilization. The reaction from the astronomical community was swift and mostly negative. Not because Loeb's math was wrong, it wasn't, but because the conclusion was so uncomfortable. Most scientists preferred exotic natural explanations over entertaining the artificial hypothesis, even when those natural explanations required their own leaps. The debate over Oumuamua data became almost as interesting as the object itself. What data had been captured, what hadn't been released? Were there observations sitting in archives that could settle the question? And how do you balance scientific openness with professional caution when you're dealing with observations that might suggest something genuinely unprecedented? We're in a similar position with 3i/Atlas, but the stakes feel higher because the contradictions are more severe. This isn't just about an unusual trajectory. This is about multiple billion-dollar instruments fundamentally disagreeing about what they're seeing. And if there's spacecraft data that could resolve it, the absence of that data from public discussion becomes part of the story. So where does this leave us with questions? Mostly. Questions that can be answered, but only if we actually pursue them. Are there psyche images of 3i/Atlas? If yes, what do they show? If no, why not? These are straightforward, factual questions. They shouldn't require speculation. They should be answerable through normal channels, FOIA requests, archive access, communication with mission teams. But until those answers arrive, we're stuck in this liminal space where the data we need to resolve the mystery might exist, but remains out of reach. And that gap between what we can observe from Earth and what might have been observed from space becomes its own kind of evidence, not of conspiracy, but of the complicated, often frustrating realities of how space science actually works. What we do know is this: if those psyche images exist and eventually get released, they're going to be examined more intensely than perhaps any spacecraft images in history. Because at this point, they're not just photographs, they're potential answers to questions that are keeping astronomers up at night. And depending on what they show, they could either calm this whole situation down or make it exponentially stranger. While we're waiting for answers about what Psyche might have seen, let's step back and ask a more fundamental question. What if we've been wrong about 3i/8/ from the very beginning? What if it's not a comet at all? Or what if we've been trying to force a square peg into a round hole? And the reason nothing makes sense is because our basic assumption about what category this object belongs to is incorrect. Let's explore the alternatives. Not wild speculation, but actual physical models that could explain what we're observing. Because if the standard comet explanation is broken, and at this point it seems pretty broken, we need to figure out what else could produce these contradictions. Hypothesis 1. The micro-outgassing body. Imagine a chunk of rock and metal from another star system, mostly inert, but with rare pockets of volatile ice trapped in cracks and fissures beneath its surface. Not a fluffy snowball like a typical comet, but more like an asteroid with ice contamination. As it passes through the inner solar system, solar heating warms these pockets. The ice sublimates, and gas escapes through narrow vents like geysers on Saturn's moon Enceladus, but much smaller and more sporadic. This would explain the JWST detections. You'd get water vapor and CO2 venting into space, creating the chemical signatures we're seeing. But because the outgassing is localized to small vents rather than distributed across the entire surface, you wouldn't get the massive dust production needed for a visible tail. The dust stays mostly buried, or gets ejected at such low velocities that it immediately falls back to the surface. Think of it like a pressure cooker with a tiny release valve, lots of steam, but no visible cloud. The problem scale. JWST's measurements suggest significant volatile loss. We're not talking about a gentle hiss of gas. We're talking about mass loss rates consistent with active cometary behaviour. To hide that much outgassing in microvents without producing visible dust requires a very specific and frankly unlikely composition. You'd need pure volatile ice somehow separated from dust particles. And geologically, that's hard to justify. Ices and dust mix when they condense from protoplanetary material. You don't naturally get clean ice bodies unless formation conditions were radically different from anything in our solar system. Hypothesis 2. The fragment swarm. What if 3? I/Atlas isn't a single object at all? What if it's a tightly bound cluster of smaller fragments, hundreds or thousands of pieces, each too small to resolve individually, all travelling together like a school of fish from Earth? We'd see them as a single point of light because they're clustered within a space smaller than our telescopes can separate. But each fragment could be producing a little gas and dust, creating the chemical signatures JWST detects. This model is actually pretty elegant. It explains why the object appears point-like. The fragments are genuinely compact, held together by their mutual gravitational attraction or possibly some kind of electrostatic binding. It explains the gas production. You have many small surfaces sublimating simultaneously. And it might even explain the unusual CO2 to water ratio. If different fragments have different compositions, and the ones richest in CO2 happen to be more active. But here's the catch. Why would fragments stay bound together over interstellar distances? We're talking light years. Even tiny velocity differences would cause pieces to drift apart. You'd need something holding them together. Their collective gravity. Maybe, if the total mass is large enough and they're tightly packed. But then you'd expect to see some structural variation over time as the cluster evolves. Some elongation, some fuzziness at the edges. The fact that 3I/Atlas remains stubbornly point-like through months of observation suggests either the fragments are impossibly tightly bound, or they're being held together by forces we don't understand. Hypothesis 3. Electromagnetic confinement. Now, we're getting into exotic territory. Suppose the dust particles around 3I/Atlas are electrically charged. Suppose there's a magnetic field or electric field strong enough to trap them near the nucleus. Charged dust doesn't follow simple ballistic trajectories. It can levitate. It can be held in place by electromagnetic forces, even when radiation pressure and solar wind would normally blow it away. We've seen this in nature. Saturn's rings contain charged dust held in complex configurations by the planet's magnetic field. Laboratory plasma experiments routinely trap charged particles using electromagnetic fields. Even on Earth, dust devils can lift charged sand grains against gravity. The physics is well understood. The question is what's generating the field around 3I/Atlas. A natural body shouldn't have strong electromagnetic fields. You need something active, something producing energy. Rotation through a magnetic field can generate currents. But 3I/Atlas is tiny and far from any strong external magnetic source. You'd need the object itself to be generating the field through some internal process. Maybe through triboelectric effects, friction between different materials creating charge separation. Maybe through radioactive decay in the core producing heat and ionization. It's possible, but it requires very specific conditions that we haven't observed in any comet or asteroid before. If electromagnetic confinement is real, though it would explain almost everything. Gas escapes because molecules are harder to trap with fields. Dust stays confined, creating a compact invisible envelope. TESS sees a point source. JWST sees vigorous outgassing. The contradiction resolves. The problem is we'd need to detect those fields, look for polarization anomalies in reflected light, search for radio emissions, find some signature that electromagnetic processes are at work. And so far, no one's reported anything definitive. Hypothesis 4, the uncomfortable one. What if 3, I/Atlas is artificial? What if it's engineered a probe, a vessel, a piece of technology from another civilization? I can feel half you rolling your eyes and the other half leaning forward. Stay with me. This isn't about jumping to aliens every time we see something weird. This is about honestly asking, what would an artificial object look like? And does 3 I/Atlas fit that profile? An artificial object could explain the contradictions perfectly if it's actively managing its heat signature, controlling what it emits and in what directions. You could produce chemical signatures without the corresponding optical features. Energy sources on board could generate gas without requiring ice sublimation. The compact appearance would be natural for a manufactured structure, no need for a fuzzy extended envelope. Electromagnetic signatures, if we found them, would be expected rather than mysterious. The problem, and it's a big one, is that this is an extraordinary claim requiring extraordinary evidence. And we don't have that evidence. We have anomalies. We have contradictions. We have observations that don't fit. But those aren't proof of artificiality. They're proof that we don't understand what we're looking at. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." That standard exists for good reason. Science has a graveyard full of revolutionary discoveries that turned out to be instrumental errors, misinterpretations, or natural phenomena that just looked weird until we understood them better. Pulsars, when first discovered in 1967, were briefly labelled LGM-1, little green men 1 inch, because their precisely timed radio pulses seemed impossibly regular for a natural source. Turns out they're rotating neutron stars. Natural, just unfamiliar. So what would actually constitute extraordinary evidence for artificiality? Each hypothesis makes testable predictions. The micro-outgassing model predicts we should eventually see some dust production faint, but detectable if we stack enough observations over time. The fragment swarm model predicts structural variations as the cluster evolves, maybe some elongation or asymmetry developing. The electromagnetic model predicts we should find field signatures, polarization anomalies, radio emissions, correlations between activity and rotation if the object is spinning. And the artificial model, it predicts things that don't occur naturally. Geometric structures, sharp edges, right angles, symmetry that nature doesn't produce, spectral lines from industrial compounds or unusual isotope ratios that stellar nuclear synthesis can't create, temporal patterns suggesting control rather than chaos activity that turns on and off at precise intervals, or that responds to external stimuli in ways that suggest intelligence. Here's what's remarkable: none of these models is a perfect fit. Each one explains some observations while creating new questions about others. The natural explanations require unlikely compositions or configurations. The exotic natural explanations require physics we haven't directly observed in comets before. Though we know the physics is possible in other contexts, the artificial explanation requires accepting something that would fundamentally change our understanding of our place in the universe. But we're going to need one of these explanations, or something even stranger, because the standard comet model is broken. We can't keep calling it a comet while it refuses to act like one. At some point, when an object consistently violates your expectations, you have to update your model of what the object is. Think about how science actually progresses. We build models based on observations. We make predictions. We test those predictions. When the predictions fail repeatedly, we don't just patch the model with ad hoc explanations. We consider whether the model itself needs revision. Sometimes that revision is minor, adding a new parameter here, accounting for an overlooked effect there. But sometimes the revision is fundamental. Sometimes you realize you've been looking at the problem through the wrong framework entirely. Continental drift was once considered impossible because physicists couldn't imagine how continents could move through solid ocean crust. The solution wasn't to abandon the observations of matching coastlines and fossil distributions. It was to realise that the ocean floor itself was moving, that Earth's crust was divided into plates floating on a viscous mantle. The framework shifted, and suddenly everything made sense. Are we at one of those moments with 3 I/Atlas? Is this object telling us something fundamental about the diversity of bodies in other solar systems, about physical processes we've overlooked, or about the possibility, however remote, that we're not alone? We don't know yet, but what we do know is that pretending everything is normal, that this is just a slightly unusual comet, isn't intellectually honest anymore. The observations are too contradictory. The standard model is straining too hard. So we're left with a choice: expand our physics, revise our models, and entertain possibilities that sound uncomfortable. Because the alternative, ignoring the anomalies because they're inconvenient, isn't science. It's just wishful thinking. And the universe has never cared about what we wish were true. So let's get concrete. Let's stop talking in generalities about exotic hypotheses and uncomfortable possibilities and actually define what would constitute proof. Because right now, we're in this frustrating middle ground where the observations are strange but not decisive. We need to draw a line in the sand and say, here's what would move us from this is weird to this is genuinely unprecedented. Think of it like a ladder. Each rung represents a level of certainty, from natural comet at the bottom to artificial object at the top. What evidence would we need to climb from one rung to the next Criterion 1 resolved geometric structure? If we could take an image of 3 I/Atlas with resolution high enough to see its actual shape, not just a point of light, but its physical form, what would convince us we're not looking at a natural body? Natural objects are messy. They're lumpy, irregular, shaped by accretion, collisions, and gravitational forces that don't produce geometric precision. Comet 67P/Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 years, looks like a rubber duck, 2 lobes stuck together at odd angles, covered in pits and cracks and boulders scattered randomly across the surface. That's what nature produces. Chaos with structure, but not design. A sphere wouldn't be suspicious. Spheres minimize surface energy. If an object is large enough and warm enough for long enough, it naturally rounds itself out. But sharp edges, right angles, geometric symmetry, those would demand explanation. A cube doesn't form naturally, neither does a cylinder. And if we saw articulated components, parts that move relative to each other, like solar panels deploying or antenna rotating, that would be unmistakable. The resolution needed to see this level of detail is actually achievable. We're talking about sub-kilometre imaging of a 440-metre object. That requires either a close flyby with a spacecraft or extremely sophisticated optical interferometry from ground-based telescopes. It's technically difficult but not impossible, and it would be decisive. One high-quality image showing geometric structure would end the debate instantly. Criterion 2. Anomalous spectral signatures. Spectroscopy tells us what something is made of by analysing the wavelengths of light it emits or absorbs. Every element and molecule has characteristic fingerprints, specific wavelengths where it interacts with light. When we point spectrographs at comets, we see water, carbon dioxide, carbon monoxide, ammonia, methane, all compounds we expect from primordial material left over from planet formation. What would make us suspicious if spectroscopy revealed elements or compounds that don't belong? Technetium, for instance, only exists as a product of nuclear reactions. It doesn't occur naturally in any significant quantities because its isotopes are all radioactive with relatively short half-lives. If we saw technetium emission lines from 3I/Atlas, we'd have to explain where it came from. Industrial compounds would be similarly damning synthetic polymers, highly purified metals, isotope ratios that nuclear processes don't naturally produce. The universe makes a limited palette of chemicals through stellar nuclear synthesis and chemistry. Hydrogen, helium, carbon, oxygen, nitrogen. These are common. Heavy elements like gold and platinum are rare but still natural, forged in supernova explosions or neutron star collisions. Anything outside that palette, anything that requires technological processes to create, would be a massive red flag. Have we done high-resolution spectroscopy of 3I/Atlas looking for these signatures? Partially. JDust has provided detailed infrared spectra. Ground-based telescopes have optical and near-infrared data, but there are gaps. Certain wavelength ranges haven't been thoroughly examined. Certain emission lines that would indicate industrial processes might be too faint to detect with current observations. More complete spectroscopic coverage would either reassure us that everything is natural or reveal something we can't explain away. Criterion 3. Multiband registration anomalies. Here's a technique professional astronomers use to study complex objects, take images in different wavelength bands, optical, infrared, ultraviolet, X-ray, and overlay them. Natural objects show predictable patterns. Hot regions emit more infrared. Dust scatters optical light preferentially in certain directions. Gas emits at specific wavelengths corresponding to atomic transitions. When you overlay the images from different bands, everything should align the way physics says it should. If the images don't align, if there's structure in infrared that has no corresponding feature in optical, or if X-ray emission is coming from a region that shouldn't be hot enough to produce X-rays, that suggests something more complex than simple thermal and scattering processes. It suggests active energy management, possibly technological in nature. We've seen hints of this with 3I/Atlas already. JWST sees a gas coma in infrared. TESS sees a point source in optical. That's a registration anomaly, though it might be explainable by particle size effects or geometry. But if we found truly inexplicable mismatches like X-ray emission from a region showing no optical or infrared activity, or radio pulses originating from locations offset from the visible nucleus that would push us into exotic territory. Criterion 4. Data provenance and authenticity. This one's about trust. If someone claims they have spacecraft images showing something extraordinary about 3I/Atlas, the first question should be, where are the raw frames? Can we verify the metadata? Can independent analysts access the data? Every digital image from a spacecraft has headers, metadata embedded in the file containing timestamps, instrument settings, exposure durations, calibration information, checksums. These headers can be verified against mission logs, cross-checked for consistency, examined for signs of tampering or manipulation. It's forensic analysis applied to astronomical data. Why does this matter? Because the quality of evidence matters as much as the evidence itself. History is littered with examples. The Apollo program's original data tapes containing raw footage from the moon landing were nearly lost, recorded over for budget reasons, requiring restoration efforts decades later. Astronomical archives have had similar issues. Mislabeled data, degraded storage media, institutional knowledge lost when key people retired. If you want to make an extraordinary claim, you need ironclad data provenance. Otherwise, you're just adding noise to an already confusing situation. Criterion 5. Correlated multi-messenger signals. This is the most sophisticated criterion, and it's based on the revolution happening in astronomy right now, multi-messenger observations. The idea is simple but powerful. Different types of signals light, gravitational waves, neutrinos. Cosmic rays tell you different things about an event because they're produced by different physics. If 3I/Atlas showed simultaneous phenomena across multiple domains, optical brightening, radio bursts, X-ray flashes, and neutrino detections, all time-locked to the same events that would be extraordinary, natural processes can produce multi-wavelength emission. We see it all the time in pulsars, blazars, supernovae. But those multi-wavelength signatures follow patterns we understand. They have characteristic correlations and time delays based on the physics of how the emission is produced. Something completely novel in its multi-wavelength behavior correlations that don't match any known natural source would demand a new explanation. It would suggest processes operating beyond what typical comets or asteroids are capable of. And if those correlations were repeatable, if they showed patterns suggesting control rather than chaos, we'd be in truly unprecedented territory. The sociology of scientific claims. Here's the uncomfortable truth: even if extraordinary evidence existed, it might not be released quickly. Mission teams face enormous pressure. Careers depend on successful missions, on publishable results, on not making claims they can't defend. The fear of ridicule is real and justified. No scientist wants to be the person who announced aliens and was wrong. The professional cost is catastrophic. Remember the arsenic life controversy from 2010? NASA held a press conference suggesting they'd discovered bacteria that could incorporate arsenic into its DNA instead of phosphorus, potentially rewriting biology textbooks. Within weeks, the paper was shredded by critics. The methodology was flawed. The conclusions were overstated. The lead researcher's career was damaged, possibly permanently. That's what happens when you make extraordinary claims that don't hold up to scrutiny. So institutions become conservative. Data gets embargoed for extended peer review. Claims get watered down to avoid backlash. National interests play a role too. Some data might be classified for reasons having nothing to do with scientific merit. The result is that even if someone has decisive evidence about 3I/Atlas, releasing it publicly might take months or years while lawyers, administrators, and cautious scientists argue over every detail. That's frustrating, but it's also understandable. Science progresses by being rigorous about evidence, by demanding reproducibility, by not accepting claims just because they're exciting. The burden of proof for an extraordinary claim is enormous, and it should be. But, and this is crucial, science has also progressed by following anomalies, by taking seriously the observations that don't fit, by being willing to update models when data demands it. We're at one of those moments. The observations of 3I/Atlas are strange enough to warrant serious attention, but not yet clear enough to draw firm conclusions. What happens next depends on whether we can access the decisive observations, whether new data closes the gaps in our understanding or widens them. The framework is there. The criteria are defined. 5 clear rungs on the ladder from weird comet to something else entirely. Now we need the observations that will tell us which rung we're actually standing on. And while we're waiting for those answers about 3I/Atlas, something else is demanding our attention, something in our own galaxy that's breaking its own set of rules and forcing astronomers to admit we still don't understand everything the universe can do. Let me tell you about something that's happening 15,000 light years away from us right now. Something that has astronomers scratching their heads because it doesn't fit into any category we've created. It's called a SAS-NJ 183209111, and it's pulsing like a cosmic heartbeat every 44 minutes. On the dot, in both radio waves and X-rays simultaneously. Why am I bringing this up when we're supposed to be talking about 3I/Atlas? Because this object is proof that the universe still has tricks we haven't catalogued, mechanisms we don't understand. And if one object in our own galaxy can break all the existing patterns, maybe we should be more humble about declaring what is and isn't possible for other weird objects we encounter. The discovery came from the Australian Square Kilometre Array Pathfinder, ASCAP for short, during a survey looking for transient radio sources. These are objects that flash in radio wavelengths, appearing and disappearing over time. Astronomers have a category for them now, long-period transients, or LPTs. They pulse every tens of minutes to hours, which is weird because most radio sources we know about pulse much faster. Pulsars, for instance, spin hundreds of times per second. Magnetars pulse in milliseconds. This slow, rhythmic behavior doesn't match anything in our textbooks. ASASN J 1832 takes it further. It's the first LPT observed to pulse in X-rays as well as radio. The data is disturbingly precise. The object emits a 2-minute burst of radio waves, then goes completely quiet for exactly 42 minutes, then bursts again, over and over, like clockwork. When NASA's Chandra X-ray Observatory looked at it, it found X-ray pulses synchronized with the radio bursts. Not perfectly overlapping, there's a slight time offset, but definitely correlated. This thing is 15,000 light-years away, somewhere in the Milky Way, but it's not associated with any obvious star cluster or nebula. It's just out there, pulsing, waiting for us to figure out what it is. So what could produce a signal like this? Let's walk through the suspects, because astronomers have been throwing every model they can think of at this problem, and none of them quite work. Magnetars are neutron stars with insanely powerful magnetic fields, billions of times stronger than any magnet on Earth. Strong enough that they warp the quantum vacuum itself. Magnetars are known to pulse as their magnetic fields twist and reconnect, releasing bursts of energy. But magnetar pulses happen on millisecond to second timescales, not 44 minutes. To explain ASASN J 1832, you'd need some completely novel configuration where the magnetic field stores energy slowly over tens of minutes and then releases it in a burst. And nobody has a convincing model for how that would work. White dwarfs are another candidate. These are dead stellar cores, stars like our Sun, that have exhausted their fuel and collapsed down to roughly Earth's size. Some white dwarfs still rotate and maintain strong magnetic fields. If you had a white dwarf spinning with a 44-minute period, and if it had active magnetic reconnection events synchronized to its rotation, you might get periodic pulses. But the timing is weird. Most white dwarfs either spin much faster once per minute or faster, or they've lost their magnetic fields entirely through billions of years of cooling. A 44-minute period is uncomfortably slow. It's possible, but it requires very specific conditions. Binary systems offer a third explanation. Maybe two objects orbiting each other with a 44-minute orbital period, with accretion or tidal heating producing periodic flares. The problem is physics. A 44-minute orbital period means the objects are incredibly close together, so close that tidal forces and gravitational wave emission should be causing them to spiral inward rapidly. They should either have merged already or be on the verge of merging. The system shouldn't be stable. None of the standard models fit. Each one requires tweaking parameters, invoking special conditions, explaining away inconvenient details. And this is where it gets relevant to 3I/Atlas. Because if ASASN J 1832, a galactic object we can study in detail, defies our existing classifications, what does that say about our confidence in classifying an interstellar visitor we've barely had time to observe on the surface? These two objects couldn't be more different. ASASN J 1832 is probably stellar in nature, a compact object left over from a dead star. Pulsing in radio and X-rays, 3I/Atlas is an interstellar comet or whatever it is, showing optical and infrared anomalies but no confirmed radio or X-ray detections. Different scales, different contexts, different physics. But here's the thing, ASASN J 1832 is proof that the universe does things we haven't anticipated. It's proof that when our models fail, It doesn't necessarily mean the observations are wrong, it might mean our models are incomplete. Before this discovery, you might have confidently said that natural objects don't produce precisely periodic signals in multiple wavelength bands with 44-minute periods. That's not what magnetars do. That's not what pulsars do. That's not what white dwarfs or binaries typically do. Except now we know it happens. We just don't know how. The discovery also highlights how much we miss. ASCAP is a relatively new radio telescope array. It's only been operational for a few years. Chandra has been in space since 1999, but it can only observe what we pointed at. ASAS NJ 1832 has probably been pulsing for thousands, maybe millions of years. And we only just noticed it. How many other strange objects are out there? Detectable with current technology, waiting for someone to look in the right place at the right time. Think about what this means for 3I/Atlas. We've been observing it for months, sure, but only at certain wavelengths, during certain windows, with certain instruments. What if it's doing something we haven't checked for yet? What if there are radio pulses too faint or too brief to have been detected? What if there are X-ray flashes correlated with its perihelion passage that no one thought to look for because, well, comets don't do that. Here's where I'm going with this. Anomalies in one object inform how we think about anomalies in another. When you find something inexplicable, you start looking for patterns across different phenomena. Sometimes those patterns reveal nothing, the objects are unrelated, and each has its own unique explanation. But sometimes, rarely, you find that nature uses the same physics in different contexts, and what seemed like unrelated mysteries are actually manifestations of the same underlying process. Could 3I/Atlas and Assassin J 1832 be related? Probably not directly. One's a stellar remnant 15,000 light-years away. The other's a small object passing through our solar system. But could they share some underlying physics? Could there be a class of phenomena we haven't recognized yet that involves strong magnetic fields and dense plasma environments, manifesting differently depending on scale and context? Let's think through what that would look like. In a galactic context, with stellar mass scales and compact objects, you get ASSN J 1832 regular pulses from rotation or oscillation, radio and X-ray emission from energetic plasma processes, NUT. In an interstellar context, with a much smaller object like 3I/Atlas, maybe the same field and plasma physics operates but manifests as confined comas, unusual gas-to-dust ratios, compact optical appearance. Maybe there are radio bursts too faint or brief to have been detected yet. Maybe there are X-ray emissions we haven't looked for because we assumed comets don't produce them. This hypothesis makes testable predictions. If 3I/Atlas and ASAS NJ 1832 share underlying physics involving organized magnetic fields and plasma interactions, we should look for faint radio pulses from 3I/Atlas, especially during perihelion when solar wind interaction is strongest, X-ray flashes correlated with optical brightening or gas production events, polarization signatures in the scattered light that would indicate organized magnetic fields, something called Faraday rotation, a twisting of radio waves passing through the coma that would reveal magnetic field strength, maybe even high-energy particle detections if acceleration mechanisms are operating. Here's the frustrating part. Most of these observations haven't been done. Radio telescopes haven't been systematically monitoring 3I/Atlas at high time resolution. X-ray observatories might not have been pointed at it during active phases. The data to confirm or rule out any connection simply might not exist yet. But even if the connection is zero, even if we observe 3I/Atlas at every wavelength and find nothing unusual beyond what we've already seen that's valuable, it constrains models. It tells us there's no coherent plasma emission, no synchrotron radiation, no radio-producing mechanism operating. That eliminates hypotheses and narrows down what's actually happening. And if we do find radio pulses, if we detect X-ray correlations, if any of the signatures we're predicting show up, that would be extraordinary. It would mean 3I/Atlas is doing something far outside the normal behavior of comets, something that connects it to active astrophysical phenomena like ASAS NJ 1832. And that would push us firmly into exotic territory, where conventional explanations no longer work, and we'd have to start seriously considering alternatives we'd rather not contemplate. The point here isn't to claim these objects are definitely related. The point is to be systematic. When you encounter one anomaly, you look for others. You ask whether there might be patterns. You design observations that could reveal those patterns or rule them out. Sometimes the wildest seeming connections turn out to have truth to them because nature, as it turns out, is pretty good at reusing the same physics in different situations. We won't know until we look, and right now, we're not looking hard enough. But that's about to change. Because there's one more piece of this puzzle that demands attention, something even more energetic, even more mysterious. That might just tie everything together in ways we're only beginning to understand. That energetic piece I mentioned, it happened deep beneath the Mediterranean Sea. On what should have been an unremarkable day, an array of underwater detectors called KM3net recorded something that, by all rights, shouldn't exist according to our comfortable understanding of cosmic ray physics. A neutrino with an energy of 220 petaelectron volts slammed through the detector, leaving a trail of light that told a story about the most violent processes in the universe. Let me put that number in perspective, because at these scales, our intuition completely fails. A petaelectron volt is 1,000,000 billion electron volts. That's already incomprehensible. So let's ground it in something concrete. The Large Hadron Collider, the most powerful particle accelerator humans have ever built. The machine that discovered the Higgs boson accelerates protons to energies of about 14 trillion electron volts. That's an achievement that took decades of engineering and billions of dollars. This neutrino was carrying 16,000 times more energy than those protons. 16,000 times. It's a cosmic bullet fired by something so powerful, so violent, that we don't have a complete theory for how it works. And it travelled across who knows how many light years of space, passed through Earth as if our planet were made of fog, and happened to interact with atoms in the Mediterranean Sea in a way that left a detectable signal. Think about neutrinos for a second. They're ghost particles. Right now, as you're listening to this, billions of neutrinos from the sun are streaming through your body, through the chair you're sitting in, through the earth beneath you, continuing out the other side into space without interacting with a single atom. They have almost no mass, so little that we're still not sure exactly how much. They have no electric charge. They have no properties that would let them bump into ordinary matter in any meaningful way. They're the universe's way of saying, "You thought you knew what matter was, think again." Detecting neutrinos requires enormous volumes of transparent material, ultra-pure ice or water, instrumented with thousands of sensors watching for the rare occasions when a neutrino does interact. When that happens, the neutrino produces a charged particle that travels through the medium faster than light can travel in that medium. Not faster than light in vacuum, that's still impossible, but faster than light in water or ice. When that happens, you get something called Cherenkov radiation, a flash of blue light, like a sonic boom but for light instead of sound. KM3net operates in the Mediterranean, using the sea itself as the detector volume. Arrays of light sensors hang on cables, monitoring cubic kilometers of water for these telltale flashes. When the detectors saw this particular event, they recorded the characteristic pattern of light, the direction, the brightness, the timing. Scientists worked backward through the physics to determine that the neutrino must have had at least 220 petaelectron volts of energy. The analysis has been peer-reviewed and confirmed. This isn't a glitch or a misidentification. It's real. Why does this matter? Because neutrinos at these energies point to cosmic accelerators operating at scales we barely understand. The most powerful candidates are blazers supermassive black holes at the centres of galaxies that are actively feeding, launching jets of plasma at nearly the speed of light. Those jets can accelerate protons to enormous energies through shock waves and magnetic field interactions. When those ultra-high energy protons collide with ambient photons or matter, they produce particles called pions that decay into neutrinos. Gamma-Ruda ray bursts are another possibility, the death screams of massive stars collapsing into black holes, releasing in seconds more energy than our sun will produce in its entire lifetime. Anything that can accelerate particles to 220 petaelectron volts is operating at the absolute extremes of physics. In environments where matter and energy and space-time itself are being pushed to their breaking points. Now, here's where this connects to 3I/Atlas, and I know it sounds like a stretch, but stay with me. Could 3I/Atlas be embedded in, passing through, or somehow connected to a high-energy astrophysical environment? The object came from interstellar space. We know its rough trajectory, we can trace it back into the galaxy. But we don't know what it encountered on its journey. Did it pass through a supernova remnant near a pulsar-wind nebula? Through regions of space where magnetic fields or plasma densities create particle acceleration zones? The speculation goes further, and I want to be clear that this is speculation. If 3I/Atlas is carrying exotic matter, or generating fields we don't understand, or has properties we haven't detected, could it interact with the solar wind or interplanetary medium in ways that produce high-energy particles? Could it seed neutrino production through mechanisms that don't operate in normal comets? This sounds absurd until you remember that we don't actually know what 3I/Atlas is. We're calling it a comet because it's in our solar system and shows some volatile activity, but everything about it is anomalous. The gas without dust, the point source appearance, the unusual chemical ratios. If it's genuinely something we haven't categorized yet, then asking whether it might be connected to high-energy phenomena isn't any crazier than any other hypothesis we've been entertaining. And here's the beautiful part, this is testable. Neutrino detectors like KM3 Net, IceCube at the South Pole, and others maintained continuous monitoring. Their data is time-stamped and direction resolved. If a burst of high-energy neutrinos occurred coincident with 3I/Atlas's perihelion passage, or with its active phases, or with any unusual behaviour we've observed optically or spectroscopically, that correlation would be significant. The chances of a random coincidence are calculable. If the correlation is strong enough, it suggests a physical connection. This has been done before with other astrophysical phenomena, and it works. In 2017, IceCube detected neutrinos from the direction of a known blazer called TXS 0506 plus 056 during an active phase. The detection was statistically significant enough that astronomers pointed other telescopes at the blazer and confirmed it was flaring across multiple wavelengths. That correlation, neutrinos plus optical plus gamma rays, confirmed that blazers are indeed neutrino sources. It was a triumph of what's called multi-messenger astronomy, using different types of signals to study the same event. Each messenger tells you something different about the source because each is produced by different physics and travels through space differently. Light can be absorbed by dust or scattered by gas. Gravitational waves require incredibly massive, accelerating objects. But neutrinos punch through everything. If 3I/Atlas is producing them, they'd escape directly, carrying information about whatever process is generating them. They're the ultimate cosmic messenger for seeing into environments that are otherwise opaque. The 220 peta-electron volt detection is proof that such messengers are out there, that we're living in a universe with processes violent and powerful enough to accelerate particles to energies we can barely comprehend. It's a reminder that our census of cosmic phenomena is incomplete. We don't know all the ways nature can accelerate particles, generate fields, produce high-energy radiation. New classes of objects, new mechanisms are still being discovered. So when we look at 3I/Atlas with all its contradictions and anomalies, we should keep in mind that the universe has already shown us it can do things we didn't predict. Assassin J 1832 pulses in ways no model fully explains. A neutrino with unimaginable energy came from somewhere we haven't identified. Black holes merge and produce gravitational waves we only learned to detect less than a decade ago. The inventory of cosmic weirdness keeps growing. Maybe 3I/Atlas is just a comet with unusual composition, and we're overthinking it. But maybe it's another entry in the catalogue of things we didn't expect. Another phenomenon that will require new physics or new categories to explain. The only way to find out is to keep observing, keep correlating, keep asking whether different anomalies might be connected. Have neutrino detectors been monitoring for correlations with 3I/Atlas? Have the timestamps been cross-referenced? Has anyone looked for bursts of high-energy particles coincident with its perihelion passage? These are straightforward questions with yes or no answers. And if the answer is no, if no one's looked yet, then we have a clear path forward look. Run the correlation analysis, check the timestamps, see if anything shows up. If nothing shows up, great. That constrains models. It tells us 3I/Atlas isn't connected to particle acceleration mechanisms. It eliminates that hypothesis and lets us focus on others. But if something does show up, if there's a statistically significant correlation between 3I/Atlas activity and high-energy neutrino detections, then everything changes. Because that would mean we're not just looking at a weird comet. We're looking at something interacting with its environment in fundamentally unexpected ways. And that brings us to something that's been complicating observations all week. Something much closer to home, but no less important to this story. The sun has been throwing tantrums. And those tantrums might be affecting every piece of data we're trying to collect. 4 coronal mass ejections launched from the sun in quick succession, all aimed at Earth. Expected arrival October 15th through 17th, 2025. These aren't gentle solar breezes, we're talking about billion-ton clouds of magnetized plasma ejected from the sun's corona, travelling through space at millions of kilometers per hour. When they slam into Earth's magnetic field, they cause geomagnetic storms, and those storms complicate everything. For aurora watchers, this is exciting news. Geomagnetic storms drive charged particles into Earth's upper atmosphere near the poles, where they collide with atmospheric gases and produce those shimmering curtains of light we call aurora. The stronger the storm, the farther from the poles the aurora can be seen. These 4 CMEs prompted forecasts of major aurora displays potentially visible at mid-latitudes. People in places like Montana, Minnesota, even northern New York might see them. Beautiful, photogenic, Instagram-worthy. For astronomers trying to observe faint objects like 3I/Atlas, absolute nightmare. The same charged particles that create beautiful aurora also create noise. Radio observations get contaminated by ionospheric scintillation fluctuations in the ionized upper atmosphere that cause signals to shimmer and fade like stars twinkling. But worse. Much worse. Cosmic ray showers increase, hitting detectors with spurious signals. Optical observations can be affected by airglow, where excited atmospheric molecules emit light that adds background noise to images, like trying to see stars from inside a brightly lit room. Spacecraft instruments face direct effects. Solar energetic particles can cause bit flips in electronics, random changes in memory that can corrupt data or trigger false detections. Star trackers, which spacecraft use for attitude control, can be confused by high-energy particles hitting their sensors and creating false stars in the image. Camera sensors show noise spikes, hot pixels, streaks from cosmic ray hits. All of this has to be filtered out during data processing, and often the filtering isn't perfect. Here's where it gets insidious. And I want you to think about this carefully. Space weather creates plausible deniability for data problems. If frames are missing from an archive, if images show unexpected artifacts, if telemetry has gaps, you can always blame the space weather. Oh, a CME hit during that observation window. Solar energetic particle event corrupted the data. The spacecraft had to go into safe mode because of the storm. All of these are legitimate effects that really do happen. But they're also convenient excuses. How do you distinguish between genuine space weather impacts and other reasons data might be incomplete or problematic? You look at the details. Space weather effects leave specific signatures. Cosmic ray hits appear as sharp spikes in single pixels or small clusters recognizable patterns. Ionospheric scintillation shows characteristic timescales and frequency dependencies that can be measured and verified. Spacecraft safe modes generate specific telemetry patterns and log entries that document exactly what happened and when. If you have access to the full metadata, the detailed logs, the instrument diagnostics, the before and after calibration frames, you can usually tell what actually happened. The problem is when you don't have access. If all you're told is data was lost due to space weather, without seeing the supporting documentation, you can't verify the claim. It might be true. It might be a simplification of a more complex situation, or it might be covering something else entirely. This isn't paranoia. This is how data integrity works in any scientific field. Scientific claims require verifiable evidence, and evidence requires provenance. You need to know where data came from, how it was processed, what happened to it along the way. When gaps appear in that chain of custody, when explanations are vague or incomplete, the data becomes less reliable for making strong claims, whether those claims are mundane or extraordinary. Historical examples. The Hubble Space Telescope's NICMOS instrument had a cooling system failure that was initially blamed on generic thermal issues, but turned out to involve specific mechanical problems that took years to fully diagnose. Mars Observer was lost during orbital insertion in 1993, with telemetry suggesting a fuel line rupture, but the incomplete data left room for alternative theories that still get debated today. When data is incomplete, explanations remain ambiguous. For 3I/Atlas observations, this matters because we're relying on a patchwork of instruments, each with their own vulnerabilities to environmental effects. Ground telescopes fighting through atmospheric turbulence and weather. Space telescopes dealing with radiation and thermal cycles. Radio arrays coping with ionospheric conditions. If all of these instruments are showing slightly different results, how much is due to genuine physical differences in what they're observing versus instrumental and environmental effects? The 4 CMEs arriving this week add another layer of complication. Any observations during this window have to account for enhanced backgrounds. Possible instrumental effects, increased uncertainty in calibration. This doesn't make the observations worthless. Scientists know how to deal with space weather, but it does mean the error bars get bigger, and bigger error bars mean more ambiguity about what's really happening with 3I/Atlas. There's also a timing question that genuinely bothers me. If decisive spacecraft observations of 3I/Atlas exist, if there are frames from Psyche or any other mission that would resolve the contradictions we've been discussing, Why haven't they been released during a week when space weather provides a ready-made explanation for any delays or data issues? It would be the perfect time to say, we wanted to release these earlier, but the CMEs complicated our data processing. Here's what we have, with caveats about data quality due to the solar activity. The absence of such an announcement is notable, though I want to be careful not to overinterpret it. Absence of evidence isn't evidence of absence, as they say, but it's also not evidence of transparency. And in science, especially when you're dealing with observations this puzzling, transparency matters. Space weather is part of what I'm calling the structural blindness we face when trying to understand cosmic phenomena. There are layers between us and the objects we're trying to study. The environment between us and the object introduces noise and distortion. The path from observation to archive introduces gaps and uncertainties. The institutional processes that govern data release introduce delays and filtering. Some of this is unavoidable physics. You can't eliminate cosmic rays or geomagnetic storms. Some of it is technological limitations. Bandwidth is finite. Storage is finite. Detectors have noise. And some of it is institutional or procedural, the way data gets handled by organizations with their own priorities and constraints. To get past this structural blindness, we need redundancy. Multiple instruments observing the same object, multiple observing strategies covering different wavelengths and timescales, multiple independent analyses of the same data using different methods and assumptions. We need transparency about what's being observed, when, about data quality flags, about processing pipelines. And we need a culture where asking questions about data provenance isn't seen as adversarial or conspiracy-minded, but as essential to doing good science. Have you ever tried to file a Freedom of Information Act request? It's not glamorous. It's bureaucratic and slow and often frustrating, but it's one of the tools available to push for transparency. And in cases like this, where publicly funded missions might have collected data about an object of intense scientific interest, FOIA requests are entirely appropriate, not because we assume malfeasance, but because sunlight is the best disinfectant. Public data should be public. The 4 CMEs this week are going to create beautiful aurora. People are going to post amazing photos online. But they're also going to create complications for anyone trying to make precise measurements of faint objects. They're going to add noise to every detector watching the sky, and they're going to provide a convenient explanation for any data gaps or quality issues that might emerge in the next few days. Which means if you're trying to make sense of 3I/Atlas, you need to be extra careful about separating signal from noise, genuine observations from artifacts, legitimate explanations from convenient excuses. You need to dig into the metadata, check the calibration frames, verify the telemetry logs. You need to be skeptical without being cynical, demanding without being dismissive, because somewhere in all that noise, in all those complicated instrument signatures and environmental effects and data processing pipelines, there's real information about what 3I/Atlas actually is. And getting to that information requires understanding not just the physics of comets and asteroids, but the physics of how we observe them and the sociology of how those observations get turned into knowledge. Which brings us to the practical question: if you wanted to actually hunt down the data that could resolve this mystery, what would you do? What specific, concrete steps could someone take right now to find the observations that might be sitting in archives, mislabeled or overlooked, or simply waiting for someone to ask the right questions? Let me give you a practical roadmap. Not speculation, not wishful thinking, actual concrete steps that someone with determination and technical skill could take right now to hunt down the data that might resolve the 3I/Atlas mystery. Think of this as a forensic investigation applied to astronomy. Step 1. Calculate the observation windows first. You need to determine the exact times when 3 I/80 would have been within viewing range of various spacecraft instruments, particularly Psyche. This isn't guesswork, it's orbital mechanics, and the tools are publicly available. JPL's Horizon system provides precise position and velocity data for solar system objects at any requested time. You can download ephemeris data for both 3 I/80 and the Psyche spacecraft, accounting for gravitational perturbations, observation geometry, everything. Calculate angular separations between the two objects. Identify visibility windows when they were positioned, such that Psyche's instruments could have observed 3 I/Atlas. Consider factors like sun angle. You can't point sensitive detectors too close to the sun without risking damage. Account for spacecraft attitude constraints. During different mission phases, spacecraft have restrictions on where they can point based on power requirements, thermal constraints, communication needs. Spacecraft often conduct routine optical navigation images, calibration sequences, engineering tests that sweep across fields of sky. 3 I/Atlas might have appeared in such observations even if it wasn't the intended target. It happens more often than you'd think. Serendipitous discoveries and data collected for completely different purposes. Step 2. Understand the instruments. Psyche carries specific cameras with known specifications. Field of view, sensitivity, spectral response, typical exposure parameters. All of this is published in mission documentation. You can find instrument papers, mission design documents, technical reports through NASA's Technical Report Server or the mission website. Download those papers, read the specs. Now calculate would 3 I/80 have been bright enough to detect factor in its distance from both the Sun and Psyche, its phase angle, any activity that might enhance or reduce visibility. Compare these predictions against the camera's documented sensitivity limits. A faint object in a wide field might be detectable with long exposures but invisible in short engineering frames. Understanding these technical constraints tells you what kind of data to expect and what might realistically have been missed for legitimate reasons. Step 3. Search the archives. Systematically, NASA's Planetary Data System hosts data from planetary missions. The archive structure is standardized but not always intuitive. Data is organized by mission, by instrument, by observation time, using naming conventions that vary between missions. You need to understand the organizational logic to search effectively. Use automated scripts. Python libraries like Astronomy and planetary_data_reader can parse PDS formats and automate searches across thousands of files. Write regular expressions that match various naming schemes that might reference 3 I/Atlas interstellar objects, calibration targets, generic field observations at the right coordinates. Download the metadata catalogs first. These contain summary information about each observation without requiring download of the full image files, making systematic searches computationally feasible. Don't just look for obvious matches. Check engineering data products, calibration frames, rejected observations that might have been excluded from primary science archives. Sometimes the most interesting data hides in supplementary collections or data marked as poor quality because it didn't meet strict science requirements, but might still contain useful information about unexpected targets. Step 4. File formal data requests. If archive searches come up empty, submit Freedom of Information Act requests. Be specific. Request all raw image frames from Psyche's cameras during exact UTC timestamps, along with accompanying metadata instrument logs and data quality assessments. Specificity matters in FOIA requests. Vague requests get vague responses or delays while agencies seek clarification. FOIA requests have to be responded to by law, though responses might be delayed or claim exemptions. Common exemptions include national security concerns, proprietary information, or data that hasn't completed standard processing. But even a refusal provides information. It tells you that data exists and gives you a reason, however legitimate or questionable, for why it's not being released. The type of exemption claimed can be revealing. Consider international data request mechanisms too. If collaborating institutions outside the US are involved, the European Space Agency, JAXA, and other agencies have their own data policies and request procedures. Sometimes data ends up in multiple archives across different countries, and accessing one path when another is blocked can work. Step 5. Cross-match with mission logs. Spacecraft operations generate extensive logs. Attitude control data showing where the spacecraft was pointing, power logs showing when instruments were active, communication logs showing when data was downlinked. These engineering records provide a detailed reconstruction of spacecraft state and activity at any given time. If the logs show the camera was on and pointed at 3I/Atlas's coordinates during a visibility window, but no images appear in the archive, that's a discrepancy worth investigating. Such gaps might indicate data loss during transmission, storage failures, or processing decisions that excluded certain observations from archival. Each explanation has different implications. Data loss is mundane but unfortunate. Processing decisions raise questions about why those particular observations were excluded. Step 6. Organize a coordinated observation campaign. While we're hunting for archival data, we should also be collecting new data. 3I/Atlas is still out there. It will have future active periods. We need coordinated multi-wavelength observations during those windows. Radio telescopes looking for faint pulses or emissions. X-ray satellites watching for flashes. Optical instruments monitoring brightness variations, all observing simultaneously. The goal is to catch correlations. If optical brightening coincides with radio pulses, that suggests electromagnetic activity. If X-ray flashes align with gas ejections seen spectroscopically, that implies specific plasma processes. If everything varies independently, that's consistent with chaotic natural activity. But synchronized behavior across vastly different wavelengths would be extraordinary. It would require organized energy release mechanisms that don't happen in normal comets. This requires coordination across facilities, advanced planning, willingness from time allocation committees to support what amounts to a high-risk, high-reward observing program. It requires convincing professional astronomers that this is worth telescope time. And that requires making a compelling case based on the contradictions we've already documented. Step 7. Citizen science involvement. Here's where you come in, not just as passive viewers, but as potential participants. Citizen science has a real role in this investigation. Amateur astronomers with backyard telescopes can contribute light curve measurements tracking 3I/Atlas's brightness variations over time. That data, collected systematically by dozens or hundreds of observers, becomes statistically powerful. Data scientists can help process archival data, write search algorithms, analyze patterns in large datasets. Legal experts can assist with FOIA processes and data access requests. People with platforms can raise awareness, pressure institutions for transparency, coordinate community efforts. The history of astronomy includes many important contributions from amateurs. Comet discoveries, variable star monitoring, supernova detections. Amateurs have found things professionals missed. Often because amateurs aren't constrained by narrow research mandates or publication pressures. The digital age makes this kind of participation easier than ever. You don't need a PhD to download PDS data and run analysis scripts. You just need curiosity, determination, and willingness to learn the tools. The 90-day timeline. Let me sketch out what an organised effort might look like. Days 1, 30. Organise, form working groups divided by skill set, orbital mechanics, archive searching, FOIA requests, observing campaigns, calculate observation windows, begin systematic archive searches, draft initial FOIA requests. Start outreach to professional astronomers willing to contribute telescope time or expertise. Days 30, 60. Compile results from archive searches. Submit FOIA requests. Prepare telescope proposals for coordinated observation campaigns during 3 Atlas's next active period. Reach out to neutrino detector collaborations requesting correlation analysis. Begin public advocacy campaign for data transparency, not aggressive, not conspiracy-minded, just firm insistence that publicly funded data should be publicly accessible. Days 60-90. Follow up on FOIA responses. Submit telescope proposals. Publish preliminary findings from archival analysis. Even if those findings are, we searched extensively and found gaps here and here. Establish communication channels with professional astronomers willing to contribute. Coordinate timing for multi-wavelength observation campaigns. This isn't fantasy. This is doable. Every step I've described uses publicly available tools, legal mechanisms that exist for exactly this purpose, and scientific methods that are standard practice. The only question is whether there's enough collective will to actually do it. Because here's the thing, the answer to the 3I/Atlas mystery exists somewhere, either in data that's already been collected and is sitting in archives, or in observations we haven't made yet but could make. The gap between mystery and answer isn't insurmountable. It's a matter of resources, coordination, and persistence. And that brings us to the final question, what's really at stake here? Why does this matter enough to go through all this effort? So why does this matter? Why go through all this effort, the FOIA requests, the archive searches, the coordinated observation campaigns for one weird object passing through our solar system? Let me tell you what's really at stake here. We're standing at a threshold, not just with 3I/Atlas, but with how we do astronomy in the 21st century. We have an object behaving strangely enough to demand explanation. We have technology capable of getting that explanation, and we have a choice about whether to pursue it seriously or let it remain ambiguous because the answers might be uncomfortable. The easy path is to call it a weird comet and move on. Patch the standard model with ad hoc explanations. Say the dust is unusually compact, or the composition is exotic, or the instruments are measuring different things because of selection effects. Comfortable explanations that let us sleep at night without questioning anything fundamental. The harder path is to acknowledge we don't actually understand what we're looking at and commit to finding out why. To follow the evidence wherever it leads, even if it takes us to places we didn't expect to go. Science progresses through exactly this kind of moment, when observations don't fit, when the standard model creaks under the weight of anomalies. You face a decision, patch it with explanations that might be true but feel forced, or consider that something fundamental about your framework might need revision. Most of the time, overwhelmingly, historically the patches work. The standard model survives, refined and strengthened. Continental drift seemed impossible until we understood plate tectonics. Pulsars seemed impossibly regular until we understood rotating neutron stars. The universe has a way of being weird but explicable far more often than it's genuinely unprecedented, but occasionally, rarely. The anomalies are telling you something deeper, something that requires rethinking basic assumptions. And you don't know which kind of moment you're in until you actually do the work to find out. Here's what we know for certain about 3I/Atlas TESS, stacked over 9000 frames, and found no extended coma, seeing it as a point source that's solid, reproducible data. Anyone can download those frames and verify the analysis. JWST and other infrared instruments detected gas emissions, carbon dioxide and water vapour indicating volatile activity. Those observations are also solid. The molecular signatures are unambiguous. Ground-based optical telescopes reported varied results, some seeing asymmetries, others seeing little structure. The observations are real, but inconsistent in ways that might reflect instrumental differences or might reflect something genuinely strange about the object. Spacecraft observations from Psyche that might resolve these contradictions have not been publicly released. We don't know definitively whether they exist. Here's what remains ambiguous: the physical mechanism producing gas without an obvious dust tail. The composition and structure of the nucleus. Whether the contradictions between instruments reflect genuinely anomalous behavior or just observational selection effects and processing differences. Whether electromagnetic or plasma processes are playing any unusual role. Whether the multi-wavelength phenomena we've discussed ASAS-N J 1832 high-energy neutrinos, any of it have any connection to 3I/Atlas. And here's what is pure speculation, that 3I/Atlas might be artificial or technological in nature, that Psyche spacecraft data is being withheld for non-scientific reasons, that there's a pattern connecting different cosmic anomalies through shared exotic physics. These ideas are worth exploring, worth testing, but they're not supported by conclusive evidence yet. They're hypotheses, not facts, and it's critical we maintain that distinction because the moment we start treating speculation as a fact, we stop doing science and start doing something else. Now, the verdict ladder. How do we move from natural comet to exotic natural phenomenon to artificial object? What evidence pushes us from one rung to the next natural is the default assumption. It requires only that we find some plausible combination of composition, structure, and environmental conditions that explains the observations without invoking new physics. Comets are diverse. We've only studied a handful up close. Maybe 3I/Atlas formed in conditions different from anything in our solar system, and that's why it behaves differently. Exotic natural requires that we identify processes operating in 3I/Atlas that don't occur in typical comets, but are still consistent with known physics. Electromagnetic confinement of dust, for instance. Unusual ice chemistry. Fragment swarms held together by electrostatic forces. These would be exotic, interesting, worthy of papers and conferences, but still fundamentally natural phenomena. Artificial requires multiple independent lines of evidence showing behavior inconsistent with any natural process. Structure indicating design, geometric shapes, articulated components, spectral signatures of synthetic materials or isotope ratios that don't occur naturally. Multi-wavelength behavior suggesting active control rather than passive response to solar heating. And critically, provenance of data that rules out error or contamination. You can't claim something extraordinary based on data you can't authenticate. 3 critical tests will move us along this ladder. Test 1: Archival Forensic Recovery. Get access to Psyche spacecraft data or any other spacecraft observations during 3I/Atlas observation windows. Verify whether images exist. If they do, examine them for structure and morphology. Authenticate their metadata and processing history to ensure they're genuine and unaltered. This is the most direct test because high-resolution images would show the object's actual appearance. Is it a typical irregular nucleus shaped by accretion and impacts? Is it a fragment cluster? Or does it show geometric features inconsistent with natural formation? One good image could resolve the entire debate. The technical barriers are low, the data either exists or it doesn't, and if it exists, examining it is straightforward. The institutional barriers might be higher, depending on data policies and institutional willingness to release observations that haven't gone through standard processing pipelines. But it's achievable through persistence and formal requests. Test 2: Decisive Multi-Wavelength Coordinated Observation. Organize a campaign during 3Y/Atlas's next active period. Polarimetry across optical and infrared bands, spectroscopy monitoring gas production, radio telescopes searching for emissions, X-ray observatories watching for flashes, particle detectors monitoring for coincident high-energy events. This comprehensive approach captures correlations that single-instrument observations miss. Does optical brightening coincide with radio pulses? Do X-ray flashes align with spectroscopic gas detections? Is the behavior periodic or chaotic? Does it produce any signatures beyond what comets should produce? Natural chaotic activity shows uncorrelated variations, different processes operating on different timescales for unrelated reasons. Synchronized multi-wavelength behavior would be extraordinary, requiring organized energy release mechanisms that don't happen in passive solar heating. Test 3 high-energy event correlation continuously monitor neutrino detectors, cosmic ray networks, and gamma-ray observatories for any statistically significant correlation with 3I/ATLAS activity. This tests the most extreme hypothesis that this object is connected to high-energy astrophysical processes. It's a long shot. Comets don't produce detectable neutrinos or cosmic rays, but the data exists in real-time streams that can be analyzed. If correlation appears, it transforms our understanding of what the object is. If correlation is absent, it eliminates an entire category of exotic explanations. The beautiful thing about these tests is that they're all doable. Not easy, not cheap, not guaranteed to work, but technically feasible with current technology and existing infrastructure. The only question is whether we have the collective will to actually do them. And that's where you come in. Every person watching this has a potential role. If you have data science skills, you can help search archives and develop analysis tools. If you have access to telescopes, even small amateur instruments, you can contribute observations. If you have legal expertise, you can assist with FOIA processes. If you have a platform or an audience, you can raise awareness and pressure institutions for transparency. If you have funding, you can support citizen science efforts. This is how modern discovery works. Not lone geniuses having eureka moments in isolation, but communities collaborating across expertise and resources to tackle problems too large for any individual. The internet makes this possible in ways that weren't imaginable a generation ago. The emotional core of this story is that we're living through a remarkable time. More cosmic mysteries are being discovered faster than ever before. The questions are getting deeper, and the answers more surprising. Whether 3I/Atlas specifically represents something genuinely anomalous or just unusual, the fact that we can study an interstellar visitor in detail, debate what it means, and devise tests to probe its nature represents a capability that would have seemed like science fiction not that long ago. And there are more interstellar objects coming. Oumuamua preceded 3I/Atlas. 2I/Borisov came between them. Statistical models suggest dozens pass through the inner solar system every year, most too faint to detect with current surveys. The Vera Rubin Observatory. When it reaches full operation, we'll find them by the hundreds. Each one is a messenger from another star system, carrying information about conditions and processes in environments we can't visit directly. Each one is an opportunity to test our assumptions and possibly discover we were wrong about things we thought we understood. We don't know which kind of moment this is yet. 3I/Atlas might be a comet with unusual but ultimately explicable properties. Or it might be the first clear example of something we haven't categorized yet natural but exotic. Or, in the scenario that sounds like fiction but can't be dismissed without evidence, it might be the first detected artifact from beyond our solar system. The probability of that last option is low, but low is not zero, and the implications are too significant to ignore just because they are uncomfortable. What we do know is this: the mystery is open, the tools are available, the tests are defined. We don't yet have proof of the impossible, but we have the strongest clues we've ever had about something that doesn't fit our understanding. The data exists somewhere in archives, in spacecraft memories, in instruments pointing at the sky right now. The question is whether we have the collective will to pursue it, the rigour to do it right, and the courage to accept whatever answers emerge. This is how discovery happens, not through sudden revelation, but through accumulated anomalies that force questions, investigations that follow those questions wherever they lead, communities that collaborate to turn observations into understanding. The 3I/Atlas mystery invites us into that process. It offers us a role in figuring out what's real and what's misinterpretation. So let's go test it. Let's demand the data, perform the observations, do the analysis, and see what the universe is actually telling us. Because the only thing worse than discovering we're wrong about something fundamental would be having the opportunity to discover that and choosing not to look. The frontier is open, the mystery awaits, and somewhere in the data we haven't seen yet, or in observations we haven't made yet, the answer is waiting to be found.